My teammate's name is Madhumita Gude, and our paper presentation is on virtualized congestion control. I will first give you an introduction to virtualized congestion control, which will give you an overview of what the authors are trying to accomplish. Virtualized congestion control happens in the network. Congestion control algorithms are implemented to reduce latency, increase throughput, and fairness in between virtual machines. This makes the client happy because they're getting the speed that they wanted, and the data center happy because this makes their business more efficient and profitable. Usually, traffic goes from various virtual machines to the data center. The authors have created a software that is controlled by the data center called the hypervisor. The hypervisor is placed on the network in between the data center and the virtual machines. All traffic will pass through the hypervisor, and within the hypervisor is the virtual congestion control layer. This is where the congestion control algorithm goes. Not all virtual machines will have the new congestion control algorithm. In order for old virtual machines to benefit from the new congestion control algorithm, we will need the hypervisor. The hypervisor is important because it translates the congestion control algorithm between the new congestion control algorithm and the virtual machines that don't have an algorithm, or even if they have their own algorithm. This means that it will seem as if all virtual machines that are connected to the data center will have the new algorithm. These legacy systems and even recent systems have their own congestion control algorithms to make themselves more efficient. When they send their data out, they think that their own algorithm is working. However, the hypervisor is located in between the data center and the virtual machines. When the data comes from the virtual machines to the data center, it passes through the hypervisor, which translates the overlay algorithm, which is the guess congestion control algorithm, and translates it and overwrites it to the data center's network's underlay algorithm. This means that the guests won't know that their data is being translated and using another algorithm other than its own. Here we can see the traditional data center setup. There are tenants containing virtual machines, which means the tenants are the infrastructures of the data center, which holds those virtual machines. Each virtual machine is a different client, and while using the virtual machine, it may seem like it's a standalone machine, but multiple clients share the same infrastructure, and these infrastructures connect to the data center. The green, yellow, and orange lines represent the traffic that passes through the data center. The data center is responsible for moving data efficiently through the network. The infrastructures have a queue, and once this queue fills up, the performance is unstable. Some of the packets get lost, and others take a long time to get to their destination. This is when congestion occurs. This is an issue because some clients will not be getting the level of service they expect. One problem with data centers is congestion occurs in their infrastructure. Congestion can also occur in just one virtual machine. In the same way, if the queue fills up for that one virtual machine, congestion will occur, causing the same problems. Data centers are not able to utilize their resources efficiently because of these issues. However, by using congestion control algorithms, we can solve this issue. The algorithms can reduce congestion on either the entire infrastructure or on a single virtual machine, allowing the packets to be sent through a shared line from other virtual machines in the same infrastructure, making the backed up virtual machine even faster than before. So congestion control algorithms have been around for a while now. The data centers and virtual machines communicate directly using these algorithms. For example, AC/DC had similar work where they modified the TCP header for every virtual machine in the infrastructure. The problem with this is that every virtual machine has to be modified for the algorithm to work. The framework that's introduced in this paper adds software in between the data center and the virtual machines called the hypervisor. Using the hypervisor, it is possible to communicate with the old legacy systems and the new systems without editing the TCP header for any other virtual machine. The hypervisor automatically translates the algorithm. There is also an ease in implementing the congestion control algorithm in the hypervisor rather than in each individual virtual machine or having to worry about legacy systems. From the test done, we can see later how efficient it is and how well it works with old legacy systems. Here we can see there are congestion control algorithms added in between some virtual machines and the data center, while others don't have any congestion control algorithms. ECN is explicit congestion notification, which was introduced in the paper. It can modify the TCP header to give notification of congestion to the sender. It also prevents packets from dropping and lets the sender send an additional message to the receiver that the packet is on the way. We will soon see a picture of how ECN enables flags to indicate support. ECN is critical to virtualized congestion control. By using them together, the VCC will be able to tell where the congestion is occurring. A queue management system such as random early detection will also be used with ECN. The issue of if the legacy system doesn't have an ECN will be solved because the hypervisor will have ECN built into it. This is how the legacy system won't know if their data is being translated because it is all done in the hypervisor after it's left the virtual machine. The authors did a congestion control test using ECN and non-ECN together. 3 tests were done with 10 flows in a shared 100 megabytes per second bottleneck link. The first test shows the good put of 9 non-ECN and 1 ECN. We can see the 1 ECN works perfectly with the 9 non-ECN. In the second test, we compare 5 non-ECN flows and 5 ECN flows. Here we can see that there's a significant difference. The ECN flows have slightly better good put than the 5 non-ECN flows and even better good put from the previous test. And the 5 non-ECN flows have decreased good put from the previous test. This is where we can see the impact of the good put between the ratio of ECN and non-ECN flows in one bottleneck link. In the third test, we compare 9 ECN flows and 1 non-ECN flow. Now we can see a huge difference where 1 non-ECN flow is starving and has almost no good put, but the 9 ECN flows are using up all the bandwidth. This shows us the ratio between ECN flows and non-ECN flows increases towards more ECN flows. The good put of non-ECN suffers. Now that we know how ECN affects good put without a hypervisor, let's get back to how the authors implement the hypervisor and how this affects ECN with newer systems in the same bottleneck link as non-ECN flows with older systems. The authors have provided a simple diagram showing how their idea will be implemented. We have a data center on the right and a guest virtual machine on the left. In the middle is the implemented hypervisor. We can see the VCC translation layer inside of it. The legacy systems only communicate between the hypervisor and guest virtual machines, which enables translation between non-ECN machines and the data center. The data center controls the congestion control algorithm, which is sent to the VCC translation layer. The VCC can then modify the previous congestion control algorithm and change it to a new one. The author's intentions in writing this paper were to deploy a new framework that can implement the congestion control algorithms without worrying if the clients have their own congestion control algorithm or even if the legacy systems don't have certain TCP capabilities. Throughout the paper, many different techniques are introduced, but the main focus is on 2 techniques: throttling the receive window, which makes the congestion window useless because it relies only on the receive window, and modifying the 3-way handshake, which requires additional techniques. There is one general method data centers can use, which is manually modifying the switches and rules to tweak the fairness, but this means that if they ever add more tenants, they will have to manually make modifications again. Let's talk about the hypervisor techniques in more detail. Another technique discussed was reading and writing into the guest memory. This can allow the hypervisor to monitor the memory state in each virtual machine. However, guests will not be okay with giving data centers ability to look inside of their memory. If there was ever a security issue in the data center, the guest security would be compromised. Splitting the connection for guest virtual machines is another technique. The TCP connection can be broken into several sub-connections, and the packet can be sent at a desired rate using the congestion control algorithm. However, this requires many buffering resources, and the TCP connection may think all the packets were received when they were not, which will cause it to advance to a next phase. This will cause errors. Duplicate acknowledgements can be sent to half the congestion window, but this violates TCP rules. Another method is to buffer the packets and acknowledgements. The hypervisor can resend the packets and buffer acknowledgements to reduce the acknowledgement sequence window, but managing these can increase latency. By throttling traffic using the TCP receive window, we can give priority to certain applications without queuing or dropping packets in the network. The throttle window will make the guest adapt to the new environment by gradually decreasing the window while monitoring the connection state. However, since the receive window throttles traffic, we don't need the congestion window anymore. This can be a viable solution for most congestion problems. However, it cannot be used if you want to make the TCP connection more aggressive. So this is the second best solution the authors present. The three-way TCP handshake is what the paper is more focused on.
So I'll be talking about the three-way TCP handshake. Now, the hypervisor can change the options negotiated when setting up the connection. That means, basically, the three-way handshake is between the guest, the state machine, and the network. And it's the way that these machines set up a connection over a TCP network. The hypervisor can change the negotiated MSS, or maximum segment size, of a packet. In case it's not clear, the MSS is the largest amount of data that can be handled at one time by device in a single piece. This figure shows the interactions of the virtual congestion control translation layer in the hypervisor with TCP traffic. So it's not the actual details of the image aren't as important in understanding how it works. The only con with the modifying the three-way handshake and changing the MSS is that they requires additional techniques to work, which is an additional overhead for the data center owner. So now I'm going to talk a little bit about the way that this proof of concept system for virtualized congestion control was implemented, because this entire paper actually was more of a proof of concept than it was an actual experiment. The data center owner introduces a new congestion control algorithm in the hypervisors, and this achieves improved fairness, performance, and control over guest bandwidth allocations. The first implementation is done using a virtual machine running Ubuntu 14.04 with Linux kernel version 3.19 or 3.13 for experiments with a 1 gigabyte per second link carried out with Mininet. And the purpose of this experiment was to demonstrate that virtual congestion control can help address unfairness between ECN and non-ECN traffic in Linux environment. And as Himalaya told you before, unfairness is about the ratio between ECN and non-ECN flows in this connection. And the importance of the implementation slides is so that we can show you the way that this experiment was carried out, and so that we can understand the conditions in which they were taking place. So ECN, or again, explicit congestion notification, allows flows to react to congestion before any data has been lost. So in the first experiment that the paper talked about, they analyzed unfairness between ECN and non-ECN flows for various numbers of ECN and non-ECN flows. So 10 senders were connected through a switch to a single receiver set to be a simple native Linux agent without virtual congestion control. The receiver can be seen as a non-ECN receiver, for non-ECN flows or an ECN receiver for ECN and virtual ECN flows. The second environment that we'll be talking about was a proof of concept system in VMware ESXi hypervisors vSwitch running on a Dell PowerEdge T610 server with 12 gigabytes of RAM and 2 Intel Xeon processors at 2.4 gigahertz. The connection flows were divided into preferred and unpreferred flows. The translation layer is configured to evenly divide available window space among unpreferred flows in absence of preferred ones. And it dynamically changes window space to preferred flows when it detects active preferred flows and divides the remainder of the space among the unpreferred ones. And this ensures the maximum efficiency for the data that's being sent through. But by controlling the end-to-end number of transmitting packets, virtual congestion control provides fine-grained data center-wide coordination of bandwidth allocation. So there were some issues with the implementation. We don't really have time to go into all of them right now, but there was complexity, hypervisor delay, hypervisor bypass. Basically, what this means is that the researchers would find certain issues in the implementation. I'm going to redo that later. Okay, so the researchers evaluated this experiment evaluated the difference between ECN and non-ECN flows. What this means is, I think we had mentioned this particular image before in the presentation, but this graph demonstrates unfairness between ECN and non-ECN flows by plotting the time series of their goodput. It shows that while ECN flows share the bottleneck equally among themselves, non-ECN flows become starved, like in part B and part C. And they cannot send as much goodput. As ECN becomes more widespread, the ratio of ECN to non-ECN flows increases, and it can send fewer and fewer packets. So the way to solve ECN unfairness is this. While ECN flows fairly share the bottleneck link among themselves, non-ECN flows can become significantly starved. The flow becomes more biased as ECN becomes more widespread and ratio of ECN flows to non-ECN flows increases. As applications increasingly adopt ECN, holdout legacy applications find it harder to get their packets through the congestion. Introducing even a small number of ECN flows into the mix breaks fairness between ECN and non-ECN flows. This is another image to show how introducing non-ECN flows impacts the flow of all the other packets. In all parameter sets, the unfairness becomes larger when there are fewer remaining non-ECN legacy flows. This is another comparison between non-ECN and virtual ECN flow. So part A in this image plots the goodput achieved with 9 ECN flows and 1 non-ECN flow, sharing 10 megabits per second in a bottleneck link, and shows how non-ECN flow suffers from unfairness. In part B, it shows how the goodput achieved this in the same setting, except that non-ECN flow is now virtual ECN. Resulting goodput of ECN incapable guest is now similar to that of its peers that are capable of ECN. Okay, so another experiment that had to be evaluated was that of the hypervisor bandwidth sharing, as Himalaya mentioned before. The hypervisor detects signature of a tenant, port, or packet and restricts the bandwidth used by this set of traffic. Bandwidth limit can be changed dynamically depending on signals from the network or the guest. After introduction of preferred flows, throughput of unpreferred flows drops due to receive window throttling, thus providing preferred flows a larger share of the bandwidth. Total throughput before and after introduction of preferred flows therefore remains relatively constant. So this graph depicts the sun window for the virtual condition control experiment. The sawtooth pattern, as you can see here, would otherwise be seen in the condition window. However, in our Linux implementation, when the receive window was the limiting window, the condition window stayed larger than the receive window for the entire experiment, which rendered the receive window meaningless. Therefore, modulating the receive window changes the size of the send window, and resulting traffic flows are very similar. So this graph, in effect, depicts a virtual ECN flow. This graph is a picture of bandwidth sharing among guests. It's the results of an experiment done where virtual condition control allocated the sharing of bandwidth and all hosts have different CCAs. So these are the throughputs for 3 unpreferred and 2 preferred flows. These flows are receive window throttled by the ESXi virtual congestion control layer. The sum of the windows of all the live flows is kept constant. As you can see that it's about the same on the top. And but the VCC throttles unpreferred flows once preferred flows start in order to give the preferred flows greater bandwidth. The authors did a great job on this paper. Many different techniques for congestion control algorithms were given before he got into methods that worked the best. The framework supplied had a great deal of information on how it works. Details were also compared with previous works and how the author improved his framework. There were a few areas where the author could have improved, such as providing more information on ECN, organization of related work, organization on implementation, and having more references and less jargon. What we learned about virtual congestion control, the thing is that we were not aware of the congestion issues that data centers faced. While this is the first congestion control framework, we learned that there were many different congestion control algorithms before, and how they were used, as well as their impacts and drawbacks, and how we can improve them. We learned of a new concept, congestion control through algorithm translation. So that was our presentation. We hope you enjoyed it, and we'd like to open the floor now to any questions you may have. Thank you.